Chapter 5, Part 2. We're going to look at thermally direct circulations, the annual average global circulation, including a simplified model called the one-cell model, moving up to a model that represents reality better, the three-cell model, and then connections between the surface and the upper atmosphere, and finally, net poleward heat transport mechanisms by the ocean and the atmosphere. To explain thermally direct circulations, we're going to use these two columns of air. They look kind of like city buildings here. So let's consider some air columns here that contain equal numbers of molecules, represented by each dot in here, that are initially at the same temperature. So if they have the same number of molecules above the surface, they have the same surface pressure, because the weight of the atmosphere above you defines your surface pressure. If I warm the column of air above City 2, which makes the air expand upward because it has more energy to spread out now, and cool the air over City 1, which causes the molecules to move more slowly and contract downward, which city has the higher surface pressure now? Is it City 1, City 2, or are they the same pressure still? Well, the actual answer is the same pressures. So long as I have not changed the total number of molecules between me and the top of the atmosphere, the surface pressures stay the same. If you cut the columns at higher levels, however, something different happens. Now, which column has the higher pressure at this level indicated by the black line? In other words, which simply has more molecules sitting on top of it? Well, you can clearly see that air column 2, the warm column, has more air molecules above this surface here, and that means that it has more pressure at that level. At this level, which way will the wind flow? As we know from the beginning of chapter 5, if you have a pressure gradient at some constant elevation, air will try to flow from high to low. So in this case, air will flow from that upper level where the pressure is higher in the warm column to the area where the pressure is lower in the cold column. What happens next is, if you're actually moving molecules from the warm column to the cold column, now you have more air molecules piling up in the left cold column. And this will change the surface pressure. It makes the surface pressure rise in the cold column. The surface pressure falls underneath the warm column because it's losing molecules to the left here. So molecules start to pile up on the left side, making the surface pressure higher. Molecules leave the right side, making the surface pressure lower. The pressure gradient force kicks in again at the surface because now you have a pressure gradient at the surface. High pressure air wants to move towards low pressure air. So again, it moves that way. And now you have what's called a thermally direct circulation, where warm air rises, comes across to the cold air column, sinks throughout that column, and then returns over to the warm column at the surface. Now we can apply this to global scale circulations, where we have warm tropical columns of air. Therefore, we have higher pressure aloft, causing a pressure gradient to move air towards the polar columns, which are cold, and lower pressure aloft. This causes more molecules to pile up in the polar columns, causing high surface pressure, and then you get a pressure gradient pushing air back towards the lower surface pressure in the tropics to get a thermally direct circulation. This is ultimately called the one-cell model of the Earth's atmospheric circulation system. It's a conceptual model where, again, you have air rising in the warm tropics, traveling aloft towards the poles, cooling, coming down to the surface, and returning the flow back to the tropics. However, that one-cell model does not include the effects of Coriolis, which we know we have because we live on a rotating planet. What you actually get with Coriolis is quite different. You do have thermally direct circulations, two Hadley cells along the equator here, where air rises at the equator, heads towards both poles, and ultimately sinks, much of which sinks near the subtropical areas, returning the flow, giving you two thermally direct circulations there. You also have thermally direct circulations at the poles, called the polar cells, where again, relatively warm air rises up at about 60 degrees north or south, and then it heads towards the poles where it gets colder, enters the colder columns there in the poles, and sinks, returning the circulation. So you have two main sets of thermally direct circulations, two for each hemisphere, the Hadley cells and the polar cells. Now if we just look at where sinking air is coming down from branches of the thermally direct circulations and where air is rising in ascending branches of the thermally direct circulations, we can get a picture of what's happening at the surface. Let's look at the blue arrows here. As air comes down from the Hadley cell in the north, it hits the subtropics. It has to spread out north and south. The part that heads south gets turned to its right, establishing what's known as the northeasterly trades. the part that heads to the north gets turned to its right, establishing surface westerlies. Both of these winds are affected by friction, which allows them to turn slightly towards low pressure. At the equator, therefore, you have trade winds converging in the equatorial low at the surface, and up here in the subpolar low, you have these winds converging with polar easterlies coming down from polar high. Again, this air is coming down, hitting the pole, all of it has to go southward. It gets turned to its right in the northern hemisphere by Coriolis and ends up converging with the westerlies coming up from the subtropical areas. So this simple model really shows you why there's surface westerlies from 30 to 60 north, why there's weak easterlies from 60 degrees north towards the pole, why there's strong trade winds with northeast component in the northern hemisphere and a southeast component in the southern hemisphere. All right, for the next concept, we're going to look at the effect of warm and cold air columns again on pressure, just to get a further understanding of this. In order to see how the height of a pressure surface relates to the mean column temperature, one must first understand that pressure decreases with height faster in cold air than it does in warm air. We're going to push these balloons upwards and see how the pressure changes at the height of the balloons. So as we're going up in the warm air column, the pressure is decreasing less than the pressure is decreasing in the cold air column. So therefore, pressure decreases with height faster in cold air columns than it does in warm air columns. The reason is pretty simple. Cold air columns have a lot more molecules packed in a tighter space. Therefore, as you go up in elevation, you're getting past more and more molecules, leaving less above you at a given height. That reduces the pressure at each level as you go up in height. In the warm air column, you have to go up substantially higher heights to get the same atmospheric pressure drop, and that's what I'm going to show next. So this simulation can show if we wanted the balloons to be at the same pressure level, that is a constant pressure surface, one balloon must change its altitude. So in order to get these balloons to be at the same atmospheric pressure, I actually have to take that cold air balloon and bring it down to a lower level to get equivalent pressures. And this is showing what's called a pressure surface. So any given pressure, you could say this is a 500 millibar pressure surface, for instance. It slopes downward. The height of that pressure surface must slope downwards towards colder air. So finally, we can also see that if we're at a constant elevation, like this black dashed line coming across here, pressure must decrease aloft from a warm air column to a cold air column. This is something we looked at with the thermally direct circulation. But it also means a constant pressure surface, if you say 500 millibars, for example, the height of that pressure surface must decrease as you go towards colder air. All right, so this concept of higher pressure aloft in warm air columns becomes important for understanding jet streams. A jet forms where the strongest pressure gradient is. If you look at the tropical air columns and go upwards in height, again, all those pressure surfaces go up higher than they do in the poles. Therefore, if you cut at a constant elevation, you have a jet stream where the strongest pressure gradient at a single elevation is. So here at the level of the jet, if you come over here, the pressure is roughly 450 hectopascals or millibars. If you go into the cold air columns over the poles, the pressure is actually more like 200 millibars. So therefore, there's a very strong pressure gradient, change in pressure over distance between the equator to poles at that height, and that forms the jet stream. The pressure gradient again tries to push the air from high to low. However, the Coriolis in the northern hemisphere would turn it to its right, coming out of the screen at us for a very strong westerly jet. And if you turn this around and look in the southern hemisphere, South Pole here, the equator here, as air tries to go towards the South Pole, it would get turned into the page. And if you think about the orientation, that actually also makes a westerly jet in the southern hemisphere. So what we're trying to do here is establish a concept of a temperature gradient at the surface affecting the height of pressure surfaces aloft and affecting the winds aloft as a result of changing pressure gradients aloft. What's shown in this image is called the polar front jet, which is a jet that's really strong as a result of temperature gradients that exist between the mid-latitudes and the poles. The red coloring is showing where that air is moving quite a bit faster, and that's the definition of the jet here. We can see the waviness of it as we go around the northern hemisphere, and this is due to really cold pockets of air coming down From the north, anytime that happens, that changes the pressure gradients aloft, and that changes the winds aloft. Essentially, the jet stream is going to be the area that splits the cold and warm surface temperatures apart because it's formed as a result of pressure surfaces that slope downwards towards cold air. So this map again establishes a link between the surface temperature gradients and the winds aloft. We'll find out in Chapter 7 that the curvature of the jet aloft and the nature of jet streaks, which are areas where the jet's increasing in speed, can affect surface pressures. And if you affect surface pressures, you can spin up storms like a cyclone, air flowing around and into a low pressure at the surface, or air flowing around and out of a high pressure at the surface. So the surface temps form a jet. Now the jet actually helps mix the temps by forming high and low surface pressure systems. They're actually quite efficient at mixing heat towards the poles and also mixing moisture towards the poles as well. So let's put all these concepts together to explain this rather complicated graph from your book. Here we have the Hadley cell. Warm air rising, heading towards the subtropics. Ultimately, it will get turned into the page here due to the Coriolis effect, so you get a subtropical jet at the northward branch of the Hadley cell aloft. The other part of the air sinks down, hits the subtropics, the return flow gets turned to its right, giving you the northeast trades. The other part that hits the mid-latitudes ends up rising over what's called the polar front, which simply means there's really cold, dense air spilling off the poles, forcing this air coming from the subtropics up and over. In the mid-latitudes, there is no thermally direct circulation. Instead, what you have, they call it a Rossby wave here, but this is essentially the jet stream moving back and forth, and that's the polar front jet that I explained a slide or two back. So as this thing curves up and down, and also due to jet streaks, again, areas where it speeds up, this creates highs and lows at the surface. An anticyclone here is a high pressure system spiraling clockwise in the northern hemisphere. A low pressure system is a cyclone here, spiraling counterclockwise in the northern hemisphere. Now it turns out that these are very efficient mixers of heat and moisture poleward, as is the meandering nature of the jet stream itself. So this is an area, although dynamically a little bit messy, pretty efficient at moving heat and moisture, again, poleward. Up here in the polar cell, again, we have another thermally direct circulation where air is sinking at the pole, heads south everywhere, gets turned to its right, so you get weak easterlies, and then a return flow as it comes up over that polar front and returns aloft. We always have to remember for the climate system, there's a surplus of radiative energy in the tropics. So a lot more incoming energy than is leaving. And there's a deficit in the poles. There's more energy leaving radiatively versus coming in from radiation from the sun. So we have to have a heat transport mechanism, and we have two of them. The atmosphere, which we're explaining here, and the ocean. They both can transport heat poleward in order to balance. One thing you have to realize, in order to get heat moved towards the poles, you can do it two ways. You can either move cold air or water towards the equator, and that would be one way of moving, ultimately getting a net transport of heat poleward, or you can simply move warm air or warm water towards the poles. They're synonymous with net heat transport. Sometimes people overlook the fact that, okay, there is some dynamics here that are definitely moving air around, but where you get the most net poleward transport is also where there's a big temperature gradient, either in the water or in the atmosphere. So you want to be mixing cold and warm air or cold and warm water with some strong dynamics to get your maximum of net poleward transport of energy. So this graph is looking at the total net energy transport expressed in 10 to the 15 watts across the northern hemisphere, starting at the equator, going to the pole. The total energy transport by the combination of oceans and atmosphere is at a maximum somewhere between 30 and 40 degrees north. The partitioning of who does the most work between the oceans and atmosphere is interesting. The atmosphere does a little bit less work than the oceans between 0 and 10 degrees north. And then the atmosphere does much less work from 10 to 20 degrees north. This is an area where the Hadley cell is a very strong developed cell. However, the temperature gradient in the atmosphere isn't that strong between the equator and the subtropics. As you go into an area where the temperature gradient is stronger, say the mid-latitudes up towards the poles, the atmosphere gets a lot of work done. And this is because those dynamics of the jet stream spinning up highs and lows are quite efficient at moving heat poleward. However, there's also a strong temperature gradient, so any dynamics can move energy. Key points for this section. The global meridional circulation, the north-south circulation, has two thermally direct circulations, the polar and the Hadley cells. The rising branches of these cells have low surface pressure and rain as a result of air rising and cooling to its dew point. The descending branches have high surface pressure and are dry, because anytime you have air descending, it warms up, making the relative humidity lower. Jets are found in the upper atmosphere above strong meridional temperature gradients. They flow west to east in both hemispheres. Now, if we really looked at the difference between what forms the jets, the subtropical jet, you have that air coming from the equator aloft, heading towards the subtropics. It conserves its angular momentum that it had in the equatorial zone, ends up getting turned to its right. That's really what forms the subtropical jet, is the conservation of angular momentum. The polar front jet, which is located around 50 or 60 degrees north and south, that's more of a function of that strong surface temperature gradient, deforming the pressure surfaces aloft. In the roughly 30 to 60 degree region, the jet streams meander and they create surface storms, both of which lead to poleward transport of heat and moisture. The poleward net heat transport by the atmospheric component is at a maximum poleward of 40 degrees, since the jet and its storms are very efficient mixers, but also because the temperature gradient is strongest there.